Hello everyone, I'm Norman Wildberger. Today we're going to carry on talking about transposes and inverses and talk a little bit about how they interact. So we're going to be working in the n by n matrices. That's an algebra. That's the framework that we're going to be talking about. It's a very nice framework because we have addition of matrices, we have subtraction, we have scalar multiplication, but crucially we also have multiplication. And we have various laws that we've already talked about. For example, the commutative law for addition. However, for multiplication, we crucially do not have a commutative law. But we have an associative law for addition. We have an associative law for multiplication. And some other laws which I haven't mentioned up to now, but I should, are the distributive laws that connect addition and multiplication. For example, a times b plus c is equal to AB plus AC, and the other way around, A plus B times C equals AC plus BC. So it's a very nice arena, and that's where we're going to be working today. And the starting point today is to recall the two kind of main results that we talked about last time, having to do with transposes and inverses of products. And if we take the transpose of product AB, that's the product of the transposes, but in the opposite order. And pleasantly, that's exactly what happens with inverses too, if we're working in the case where A and B are invertible. So if A and B are invertible matrices, that is, we're assuming that they do have inverses, then their product is also invertible, and that product is in fact the product of the inverses, but in the opposite order. So we have some consequences of that. So for example, if A, B, and C are in n by n matrices, then if we have the product A, B, C, its transpose is going to be, well, we can write it first as the product AB times C, so it's a product of two matrices now. Then the previous rule applies, so we get the transpose of the second one, C transpose, times the transpose of the first one, AB transpose. And then the AB transpose becomes B transpose A transpose. So we end up getting that ABC transpose equals C transpose B transpose A transpose. And then this extends to products of K matrices. For example, if you have A1, A2 up to AK, the transpose of that will be AK transpose times AK minus 1 transpose, all the way up to A1 transpose. Now, a very similar thing happens with inverses. So if matrices are invertible, then the same patterns appear. So exactly the same argument. If A and B and C are invertible, for example, if we have three of them, then the product A, B, C, its inverse is going to be, well, it's exactly the same argument. Will give us C inverse times B inverse times A inverse. And that will also be invertible. And we can generalize that to products of K matrices, as long as they're all invertible. So if A1 and A2 all the way up to AK are invertible, then the product A1 times A2 times AK is also invertible. And indeed, we can write down the formula for it. A1, A2 up to AK. The inverse of that is AK inverse times AK minus 1 inverse down to A1 inverse. All right, so we have that nice kind of relation, just as we did corresponding relation for transposes. All right, so here's a little problem. So simplify the following kind of formidable looking expression. We have here, A transpose, B transpose times C, and we're taking the transpose of all of that, and we're multiplying it by BA inverse. And we're assuming that A, B are invertible and that all the matrices are n by n matrices. Okay, so let's have a look. So we have A transpose B transpose C transpose of all of that times BA inverse. We have to simplify this. So that first expression, A transpose B transpose C transpose, the product, that will be the product of the transposes of the various things, but in the opposite order. So we're going to get C transpose, and then B transpose transpose, and then A transpose transpose. While BA inverse is A inverse times B inverse. But now, what is B transpose transpose? If you take the transpose of the transpose, you get back the original matrix. So we get CT times B times A times A inverse B inverse. And on my right, since B transpose transpose equals B, etc. Okay, but now remember we're dealing with matrices and we have associativity, so we don't need these brackets. We don't need to bracket things, so we can just write it out as a product. C transpose B, A inverse, B inverse. And when we do that, we can then bracket the middle A terms, A times A inverse. We can multiply them together first. Okay. When we do that, we get the identity matrix, the n by n identity matrix actually. And then when we say bracket the identity matrix with let's say this one here, then we're going to get C transpose B just times B inverse. And then the B times B inverse gives us the identity matrix again, and we just end up with C transpose. So the whole thing simplifies to C transpose. Now, we have these two operations, transposes and inverses. How do they interact? Well, here's a proposition. That if A is an invertible n by n matrix, then so is A transpose. And in fact, its inverse, the inverse of A transpose, is equal to the transpose of A inverse. So let's prove this. Proof. So we want to show that A transpose is invertible and that A inverse transpose is its inverse. So let's take A transpose and multiply it by A minus 1 transpose. How can we simplify that? Well, it's a case of doing the same kind of thing that we were doing previously, but kind of doing it in reverse. Here is a product of two transposes. And so we can write it as a transpose of a product by putting the second matrix first and then the first matrix second and taking the transpose of that entire thing. But when we take A inverse times A, we're getting the n by n identity matrix. So we just get the transpose of the identity matrix. And I remind you that the identity matrix looks like this. It's got ones down the diagonal and zeros everywhere else. So when you take its transpose, you just get the identity matrix. It is a symmetric matrix. It's equal to its own transpose. And what does that tell us? That tells us that if we want to know what the inverse of A transpose is, well, here it's going to be. Okay. And similarly, you can check that A inverse transpose times A transpose on this side is also the identity matrix. And so A transpose is indeed invertible. Invertible. And its inverse is indeed A to the minus 1 of t. So this gives us another way of sort of simplifying when you have transposes and inverses together. You can interchange the transpose and the inverse. Whether you take an inverse first and then take the transpose, or you take the transpose and then the inverse, it's going to be the same thing. Okay, so I just want to mention a few sort of special kinds of matrices, or special classes of matrices, special, say, n by n matrices involved in these notions of transposes and inverses. So I guess we've already talked about the invertible matrices. The invertible matrices. These are the matrices A, such matrices A whose inverses exist. So that's a class of matrices, right? Not all n by n matrices are invertible. So for example, I give you a 3 by 3 example, which is not invertible. Suppose you have some matrix 1, 2, 3, 0, 0, 0, 4, 5, 6. Let's call it A. This is not invertible. How do I know it's not invertible? Well, let's say I want to multiply it by anything. Suppose I have 1, 2, 3, 0, 0, 0, 4, 5, 6, and I'm multiplying it by some 3 by 3 matrix. Okay, what do I know about this product? Well, what I do know, without even making any computations, is that this row here, if I multiply this row by this column, I'm going to get 0. So there's going to be a 0 in the middle here. And if I multiply that same first row by this second column, I'm going to get a 0 beside it. And if I multiply it by the third column, I'm going to get a 0 beside it. So whatever I get is going to have this form here. I know that there's going to be a row of zeros. The row of zeros here guarantees that there's going to be a row of zeros over here. And in particular, this is not equal to the 3 by 3 identity matrix, because the 3 by 3 identity matrix has a 1 in that middle, that 2, 2 entry, the middle entry in that second row. So there's no way that I can multiply this matrix by anything and get an identity matrix. That's the reason why A is not invertible. So telling whether a matrix, like a bigger matrix, is invertible or not is maybe not entirely obvious. In fact, we'll see that it's not at all obvious. Okay, there's not a very easily computable criterion. We'll see that ultimately the determinant controls that, but the determinant is a little bit computationally intensive, so it's not just immediate. You can't just look at it. In this case, you can look at it because there's a row of zeros, which makes it obvious. Okay, so this is one important class of matrices. So inside the world of matrices, the invertible matrices, okay, are a very important class. They're the ones that you can divide by. They're the ones that you can do arithmetic a little bit more smoothly with. Okay, what about some other classes of matrices? Well, how about symmetric matrices? So these are matrices that have the property that their transposes are equal to themselves. And then there's a kind of a corresponding class called the skew-symmetric matrices. They have the property that their transposes are equal to negative of themselves. Can we give some examples? Okay, so let's look in the 3 by 3 case. In the 3 by 3 case, let me show you what a typical symmetric matrix looks like. A typical symmetric matrix has the form, okay, it's going to be 3 by 3, and the diagonal elements can be anything they want to be, A, B, C, let's say. And the off-diagonal elements have to be corresponding because this matrix has to be equal to its transpose. So this D here has to be matched with the D below it. Maybe there's E up here, then there has to be an E here. If there's F here, then there has to be an F here. So this is your general expression for a 3x3 symmetric matrix. This is what it looks like. And we can see that there's a kind of a 6-dimensional space of these things, right? There's sort of 6 parameters that describe these symmetric matrices. How about skew-symmetric matrices? So a typical skew-symmetric matrix has the form skew-symmetric matrix. Okay, that turns out in the 3x3 case to have zeros along the diagonal. And then on the off diagonals, if that's D, then that's going to be minus D. If that's E, that's going to be minus E. If that's F, that's going to be minus F. So that's actually kind of your generic 3x3 skew-symmetric matrix. In this case, we see that there's essentially 3 parameters for the space of skew-symmetric matrices. I'll leave you, here's a little exercise, that if A is an n by n matrix, show that, let's say, B, which is A plus A transpose over 2, is symmetric. And say C, which is A minus A transpose over 2, is skew-symmetric. And you can also show that A is B plus C, which shows us that we can write every matrix A as a sum of a symmetric matrix and a skew-symmetric matrix. It's kind of a pleasant little exercise. So finally, I want to talk about one more class of interesting matrices, which are a little bit more advanced, okay? Because we're going to put the idea of transposes and inverses together, still in the n by n case. So we say that an n by n matrix is orthogonal precisely when it's, let's say the matrix is A. An n by n matrix A is orthogonal precisely when its inverse is equal to its transpose. Its inverse equals its transpose. That's kind of interesting. So what would be an example of that? So in the 1 by 1 case, could we cook up an orthogonal matrix, a 1 by 1 matrix whose inverse is equal to its transpose? Well, transpose in the 1 by 1 case is not going to do anything. The transpose of a 1 by 1 matrix is itself. So this would really be just saying that the inverse of the matrix is itself. Well, here's an example. If A is the matrix 1, its inverse is 1 over 1, which is itself, which is its transpose. Or here's another example. A equals minus 1. And I'll let you think about it. And these are the only examples. These are the only 1 by 1 orthogonal matrices. How about in the 2 by 2 case? In the 2 by 2 case, can we write down an orthogonal matrix? Well, let's have a look at this. So suppose I write down the matrix 3/5, 4/5, minus 4/5, 3/5. Okay, let's check. Is that going to be orthogonal? So claim this is orthogonal. Well, let's check that. What does that mean? So I need to convince you that its inverse is equal to its transpose. How am I going to do that? I'm going to calculate A times A transpose. So that's 3/5, 4/5, minus 4/5, 3/5. And its transpose will be 3/5. Okay, we have to put a minus 4/5 up here, 4/5 down here, and 3/5 here. So if I take that product, what am I going to get? 3/5 times 3/5 is 9/25. 4/5 times 4/5 is 16/25. 9 plus 16 happens to be 25, because it's really like a 3, 4, 5 triangle, isn't it? 3 squared plus 4 squared equals 5 squared. That's telling us that this top entry is actually 1. Below it, we get minus 4/5 times 3/5 plus 3/5 times 4/5. Well, that's 0. Up in the right corner, we get minus 12/5 plus minus 12/25 plus 12/25. That's also 0. And on the bottom, we get another 16/25 plus 9/25. That's also equal to 1. Okay, and I'll leave to you to check that the same is true when you get A transpose times A. So that means, therefore, that A is invertible, and its inverse is indeed this A transpose matrix. So A is orthogonal.